Good day everyone, I'm Maria Margaret Pacheco. Today we will explore what mathematics is all about, specifically the different personas, terms, inventions, and theorems that relate mathematics have to go through as the years go by. What are you waiting for? Allow me to let the information spread. The earth is evolving, many generations are coming, and as the world evolves, more things expand around us. Same goes for mathematics. A lot of things cannot be solved without the help of defining numbers, solving formulas, determining mathematical systems, and etc. Many years before mathematics was discovered, people were in the use of the old style of determining amounts. Perhaps, at the time, the amount and terms for counting wasn't yet discovered, and what people used all the time was to familiarize things using symbols and other things such as clays and tokens, to identify whether their belongings are complete or incomplete. Furthermore, I'll introduce you to one of the greatest mathematicians. His name is Johann Carl Friedrich Gauss, also known as the Prince of Mathematicians. He was a German mathematician, astronomer, geodesist, and physicist who made greatest contributions to the field of mathematics and science. He was famous for his quote, "Not notations, but notions," which tells us that we should be able to focus on expanding our understanding on how mathematics works, instead of just looking at number symbols. Next is discoveries of numbers. Numbers with a combination of digits 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 are called Indo-Arabic numbers, which we are using in today's world. It was introduced by Leonardo Pisano, also known as Fibonacci in Europe, within the 12th century. He was educated in North Africa, then later brought his knowledge in Italy, the Indo-Arabic numerals, in which, according to Archimedes' laboratory, Hindu numeral system is a pure value system. That is why we need to use 0. Now let us proceed to the use of symbols for numbers. Numbers started in a single tally mark, which was the earliest evidence of the use of numbers. It was when the civilization settled and agriculture developed where tally was used in order to measure plot lands and individual taxation. For example, the Shang stick. It was the first pocket calculator ever known. The tally in the stick represents the prime numbers and some duplication series, 3 to 6, 4 to 8, and 5 to 10. As you can see in the picture, there are the vertical lines that would best represent the quantity of a certain object. Did you know that before discovering how to count numbers, there are other things that can be used to familiarize an amount, such as hands, clay, and tokens. Using of hands wasn't really intended to count it by sequence. Rather, it was used to just simply represent each fingers for each object. Long time ago, people could say, "I have 2 hands and a thumb of camels," in which they fold their fingers by glancing at the camels at the same time. In addition, they also use tokens to measure their animals by dropping 1 token for each animal that would pass through them. Aside from hands and tokens, there are a lot of things that people from the past used in order to measure things such as clay, pebbles, wood or bone, and etc. Next is fractions. It came from the Latin word fractio, meaning to break. It was symbolized by using slash or dividend symbols in which it was divisible. In Egyptian mathematics, they only make use of addition and have the multiplication and division. Around 1800 before Christ, fractions were being used by Babylonian cultures. Fractions weren't all about counting, rather than you can also remember things in a fraction form. For example, the 2 siblings own 3 businesses, which in fraction can be formed as 2/3. That's how useful fractions can be in terms of remembering or symbolizing things wherein it makes complicated things look easier to understand. Moving on to the concept of 0, invention of symbol for nothing. In between 400 and 1200 AD, the concept of 0 was accepted, although the main inventor was never known. It was introduced from the well-known Aryabhata, who was at the time a famous scientist, astronomer, and a mathematician. The scientists introduced zero and a decimal number system during the 5th century and used it as a placeholder number. Then later on, in the 7th century, Brahmagupta described the rules for zero. Also, we have invention of negative numbers. As the concept of numbers evolved, new terms are being added in the field of mathematics, specifically the invention of negative numbers. Negative numbers are most used in loan, debt, and transactions. Also, we have invention of negative numbers. As the concept of numbers evolves, new terms are being added in the field of mathematics, specifically the invention of negative numbers. Negative numbers are most used in loan, debt, and any other transactions.
At its core, mathematics is about discovering and understanding patterns, relationships, and structures in the universe. It's a language for expressing and formalizing concepts from the most abstract realms of theoretical physics to the practical applications in engineering, economics, and beyond. Mathematics is not only a tool for solving problems, but also a way of thinking logically and critically. It provides a framework for precise communication, modeling complex systems, and making informed decisions. Mathematics is more than just numbers. Mathematics deals with abstract structures, patterns, relationships, and logical reasoning. This includes the fundamentals of logic, transformation, symmetries, tessellations, and fractals. While numbers are a fundamental aspect of mathematics, the discipline encompasses a vast array of concepts beyond numerical calculations. In this chapter, they introduce the most powerful general weapons in the mathematician's armory, which is started by Ian Stewart, the thingification of process, or in the dictionary form, reification. It is a concept that refers to the representing abstract processes or phenomena as tangible objects or entities. In mathematics, this concept often manifests in the form of mathematical models where complex processes or systems are represented using mathematical structures such as equations, graphs, or diagrams. By thingifying processes, mathematicians can analyze, manipulate, and understand these processes more effectively. For example, in calculus, functions are often treated as things that can be differentiated, integrated, and operated upon to understand the underlying processes of change or accumulation. However, mathematicians are not the only people who play the thingification. The legal profession talks of theft. Similarly, in computer science, algorithms are thingified as code or data structures to describe computational processes. Overall, thingification of processes is a powerful abstraction technique that enables mathematicians and scientists to study and manipulate complex phenomena in a more concrete and manageable way.
Hi everyone, I am Julie M. Alava from the IR1A, and I am here today for giving you some idea about Principia Mathematica. Mathematical discoveries have been used in various cultures since the beginning of recorded history. The concept of a set was first introduced in the book Principia Mathematica by Bertrand Russell and Alfred North Whitehead. The book aimed to examine the logical organizations of mathematics and develop data structures for the key concepts. However, it lacks the interaction between mathematical ideas. The inventor of mathematics delves into unsolved riddles and constructs routes for broader public access. Principia Mathematica, often abbreviated PM, written by Bertrand Russell and Alfred North Whitehead, and published between 1910 and 1913. This three-volume work focuses on the philosophy of mathematics, particularly the concept of logicism. It aimed to show that all of mathematics could be derived from the basic principles of logic. PM or Principia Mathematica is known for its complex symbolic notation and its attempt to solve logic paradoxes like Russell paradox. Principia Mathematica, Theory of Descriptions by Russell, introduced in 1905, aims to eliminate logical awkwardness by translating propositions with definite descriptions into expressions that do not. This technique was gaining significant traction among philosophers, including those not interested in mathematics. Principia Mathematica aimed to prove mathematically what the principles of mathematics agreed for philosophically. While its formal proof have been widely accepted, its philosophical significance remains debated. It argued that mathematics is logic if the theory of types is a logical theory. According to Kurt Gödel's 2021 completeness theory proved that a single logical theory cannot derivable all of mathematics. The goal of Principia Mathematica was to demonstrate the logical underpinnings of mathematics, or that the fundamental ideas and methods of thinking that underpin mathematics can be defined in logical manner. It translates propositions with definite description into expression without them removing logical awkwardness. Originally developed to overcome contradiction in his logical theory, this method has become influential even among philosophers without mathematical interests. Russell's and Whitehead's Principia Mathematica, ambitious attempt at logicism that aimed to unify mathematics under a single logical system, offering a rigorous foundation for the subject, influenced development of formal logic that symbolic notation introduced in PM or Principia Mathematica, helped shape modern logic and raise important philosophical questions while ultimately incomplete due to paradoxes. PM's work on logic continues to be studied for its contribution to the philosophy of mathematics.
For the discoveries of mathematical equations, formulas, etc., there is no doubt that mathematicians have dealt with trial and error scenarios and worst of all, frustrations. It is what they peg as the face of the mathematician's existence. You have what it takes to convey a story, but you don't see a convincing storyline worthy of proof, and you are lacking some key idea that would widen the areas of the problem. This concept correlates the shape or Dach theorem. If you look at it, it's really hard to figure out how this theorem works, and evidently you'll feel frustrated about not achieving your desired outcome. According to the aforementioned theorem, the words ship and Dach have the same vowel in two different locations. If a C is substituted for the letter I, the first word can transform into the second. The word won't have any letter without any vowels, though if there is already one in it. Therefore, without at least one intermediate word with two vowels, it is practically impossible to go from ship to Dach. The only way to avoid ever having a two-vowel word is if the vowel positions in the original and final word remain the same. According to the previous hint given, since ship only contains one vowel that alternates between positions 3 and 2, it cannot completely disappear. Because it is illegal to change two letters, you cannot accomplish that by simply changing one letter. Instead, the vowel at position 3 and the consonant at position 2 must be switched all at once to the consonant at position 3 and the vowel at position 2. With that being said, this is where the inclusion of creative mathematics started. Its concept is similar to the aforementioned concept, but it has a deeper and more serious context. Going back to the ship or Dach theorem, it shows how mathematicians use a formal style to conclude a reasonable and convincing story. It has taken a toll on mathematicians' ability to perform or tell a convincing story with an illustration of the difference between genuinely convincing arguments and hand-waving arguments. Thus, it has sparked a great phase of frustrations for them, as they have wanted to be the first to have their discoveries known. Hence, as we all know, some articles have it that for a discovery to be liable and argumentative, it should come with proof to guarantee its credibility, accuracy, and logical assumptions of the corresponding conclusion. On this matter, we can use previously established statements, and this is where theorems comes in, like the ship or Dach theorem. But on every proof, the usage of original assumptions, known as axiom, along with their accepted rules is justifiable and certain to make all of this beneficial. Proofs are examples of exhaustive deductive reasoning. which establishes logical certainty to be distinguished from empirical arguments, or non-exhaustive inductive reasoning, which establishes reasonable expectation. A proof does not merely show that a statement is true in a large number of cases. Rather, it must show that it is true in every possible scenario. Unfortunately, there are some cases where numerous pieces of evidence led to a completely wrong answer. One example that comes to mind is the concept of prime numbers, which was known for the numbers 2, 3, 5, 7, 11, and goes on forever. It led to a completely wrong answer, shifting from the idea of having more primes in the 1 less than in the 1 more to 1 more than a multiple of 4 class goes into the head. It was also proven that primes get sufficiently big and that they don't settle in having less or more values. Big prime numbers are the sort of thing amateur mathematicians became obsessed with, and this becomes infeasible, so you need some serious computing power. Hence, this is not what it's all about. It is about a hypothetical thought of mathematical proof having no guarantee of arriving at the correct conclusion. The brighter part of all of this is that large numbers can acquire rare situations in the possibility of exceptions with or without assurance of the right or wrong answer. Still, the odds are 1 in a trillion, and the simple wrong step could destroy all of them. This teaches us the lesson of making sure of everything and fact-checking. Mathematics is hard to puzzle with, and it even gets harder if wrong patterns are made. Hence the sureness of having everything laid out to be right and certain. Even mathematicians make mistakes on this matter. But if all things are done with certainty and conviction, everything will fall into place, and if the odds are ever in your favor, everything will be correct, and they will all praise you for the correctness of your work. Thank you so much for watching this vlog. We hope that you have learned something from it, and we hope that you will stay tuned for the next. Thanks!